Hello everyone, I'm Usman and I will be presenting Leo. Leo is a system for online machine learning based traffic classification and it operates at multi-terabit line rates. This work was done at Purdue University in collaboration with my amazing advisors, Sanjay, Vishal, Shrivastav, and Mohit, Tawarmalani. To begin, let's ask the question, why do we need machine learning based traffic classification? Well, it is used for a number of traffic classification tasks, including identifying security anomalies, identifying IoT devices for preferential routing, and for identifying applications that exist in the network traffic. There has been a lot of interest in ML-based traffic classification in recent years for two main reasons. One, its ability to capture complex patterns without peeking into the packet payload, and two, its ability to learn behavioral patterns from network flow statistics. And these two reasons combine and make ML-based traffic classification applicable to encrypted traffic. So what are the limitations of the state of practice? Let us look at an intrusion detection use case, starting with a network core. To inspect all traffic, we place taps in all of the network links, which then replicate this traffic and forward it to an aggregation switch. This switch then forwards this traffic to an IDS cluster. Now, when an attack happens, it results in a slow asynchronous feedback loop. So in summary, it is challenging to perform traffic classification at line rates. So this leads us to our research question. Can we come up with something that can do traffic classification for every packet at line rate? We focus on exploiting opportunities with programmable switches. These switches allow users to define custom packet processing logic, which is then executed at line rates. So our goal is to use the programmable switch to inspect every single packet in real time, thereby reducing the traffic that is offloaded to the off-path IDS cluster. So for example, we may use the programmable switch as an initial filter, where the programmable switch may be used in conjunction with an IDS cluster, and the switch then acts as an initial filter, flagging potentially malicious traffic, and then replicating and forwarding it to the IDS cluster for deep packet inspection for more thorough analysis. And this IDS cluster only analyzes a smaller subset of the traffic, thanks to the switch acting as an initial filter. But there are a few key challenges with deploying ML to programmable switches. Firstly, we want the ML models to be runtime programmable. This means allowing updates to the model that is currently deployed without any network downtime. Secondly, we want the ML model to be resource efficient. Because switch hardware resources are reserved at compile time, knowing the worst case upper bound on the resource that will be used is very important. And finally, programmable switches are known to have limited expressivity, such as the lack of multiplication and division, which makes it hard to deploy ML models to programmable switches. For that reason, our focus is on deploying decision trees to the programmable switch, because programmable switches already have sufficient expressivity to deploy these models. Also, decision trees are known for being easily interpretable compared to other ML models. And finally, decision trees have been shown to have competitive accuracies as compared to other complex ML models. So what is Leo? Leo is a traffic classification scheme that supports a class of decision trees in a runtime programmable manner, supporting any tree within that class while also allowing updates from one tree to another without any switch downtime. Leo is also scalable in terms of the number of ALUs, the switch stages required, and the total memory. Our evaluations show that Leo scales to large depths that are twice as deep as the state of the art, while also managing a large number of concurrent flows. Finally, Leo is also highly accurate, and our evaluations show that the classification accuracy is comparable to a server-based scheme. So prior work on deploying decision trees to programmable switches can be placed into two buckets. One which follows the natural tree dependency when mapping to the switch. These works use less memory, but they're bottlenecked by the number of available switch stages. On the other end of the spectrum, to address this switch bottleneck, there is easy, which tries to break the tree dependency, thereby reducing the number of switch stages required, but at the cost of more memory. So this leads us to the question, how bad can this memory use get? To understand this, we have presented some analysis in our paper to explore the memory requirement to provision for all trees within a class, and we find that it is prohibitive. Based on our analysis, we present two key results. Firstly, the total SRAM to provision with easy is exponential in the number of features. And secondly, we find that there is a special class of trees that only has a polynomial number of leaves, but it requires reserving an exponential amount of TCAM rules in the switch. We defer the full analysis to the paper. So how does Leo work? The workflow is as follows. The user starts by specifying a tree specification or the class of tree that the user wants to support. Then the Leo compiler chooses a representative tree structure for this class of trees. And then it provisions resources against this special tree structure in the switch data plane. Finally, at runtime, the switch control plane can be used to reconfigure any tree within that class of trees that the user specified. So now, let us take a closer look into how Leo works. To enable runtime programmability, we need to build something that allows both the node feature and the constraint to be modified at runtime. To enable this, Leo provides a multiplexed ALU abstraction that allows a set of features and a set of constraints to be compared against each other to execute a single decision node of the tree. So now to build a runtime programmable tree, we can simply reserve one of these mux ALUs against every decision node in the tree, thereby coming up with a fully runtime programmable tree. But there is a catch. These ALUs are scarce in the programmable switch. And reserving one mux ALU for every decision node in the tree results in a prohibitively large resource requirement. Which leads us to the question, how do we make these ALU requirements more tractable? So following from the previous question, we make a key observation, which is a packet only accesses a single decision node per tree level. So in the example shown, if we focus on the third level of the tree, there are 4 possible nodes, but this packet only encounters the f less than 5 node. So the insight here is that we should allocate resource for only one node per tree level. And then at runtime, we multiplex the feature comparison to use based on the path that that packet took through the tree. And so we're, instead of reserving one mux ALU against one decision node, we're now simply reserving one mux ALU for an entire level of the tree, thereby improving the ALU resource efficiency by a lot. But node multiplexing has a key limitation. Because each layer of the tree is being mapped to one mux ALU, each layer of the tree ends up using up one stage of the switch. And hence, the depth of the tree that can be supported on a switch is limited by the number of available switch stages. And in the programmable switches available today, the number of stages is only a handful. Which leads us to the question, how do we scale this tree depth? So to address this, our key idea is to perform multiplexing at the granularity of subtrees rather than individual nodes. Using these subtrees, we come up with a technique we call subtree flattening and multiplexing, which works in 3 key steps, which we will look at now. So first, we identify the subtrees in a given class. So in the example shown, we have created 5 subtrees with 3 nodes each. And next, we flatten the subtree, with the goal being to execute more of these decision nodes in parallel within one stage. So this means, like, unlike the previous approach where a single layer of the tree was mapped to one mux ALU, now we map as many nodes to one stage as there are in the subtree. So next, so by doing this, we can execute 3 ALUs within one stage. So next, we need a mechanism to combine the individual results of these mux ALUs. And the reason we need this is to decide what action to take for this subtree. Now, this action could be as simple as terminating execution if a leaf node is encountered, or perhaps deciding which subtree to execute next. So for this reason, we make use of a binary table that is keyed by the outputs of the mux ALUs in the subtree. Note that in addition to the outputs of the mux ALUs, the table is also keyed by a state. This state is tagged along the packet in its metadata, and it's used for tracking which subtree did the packet originate from in the previous level. So far, we have only built a mechanism to support the yellow highlighted subtree. But at runtime, a packet may encounter any of the other subtrees that are on the left. So we need a way to multiplex subtrees as well. So for this, Leo uses the multiplexed ALU abstraction we presented earlier. So if we consider the yellow and purple subtrees, Leo first feeds the information of the yellow subtree to the multiplexers, and also the information for the purple subtree to the multiplexers. So by doing this, using just 3 ALUs, we are able to support both the yellow and the purple subtree. And the same process applies to the other subtrees as well, allowing us to reuse the same 3 ALUs. Finally, we add some more entries to the binary table to support the purple subtree's outputs. So in this example, for a subtree of size 3, subtree multiplexing and flattening has resulted in a halving of the stage requirement. And note that for larger subtrees, the reduction in switch stages required would be even larger. So in general, it is a factor of log k reduction, where k is the number of nodes in the subtree. Finally, when mapping to the Tofino switch, we encounter a few implementation challenges, which I will very quickly cover right now. So handling stateful features while making efficient use of the pipeline stages is difficult because flow state is expensive. Handling transient states to ensure that the tree executes correctly when a tree update is in progress is another challenge that we address. And finally, we also present an optimization that further reduces the stage requirement in half when we use the TCAM memory. We present details of these in the implementation section in the paper. So in order to support a class of subtrees, the resource requirement for Leo has to be within a respectable upper bound. So we find that for subtrees of size 3, the number of SRAM entries required is a polynomial with the number of internal nodes, whereas with easy, it was an exponential with the number of features. We include more analysis in the paper, including expressions for the number of rules required with TCAMs, and also for more general subtree sizes equal to k. So for evaluation, we compare Leo to prior work, Easy, pforest, and switch tree. And our methodology includes deploying each of these schemes to the Tofino switch and finding what class of subtrees each scheme supports, and within each scheme, finding the classification accuracy of the best performing tree. We do this for true intrusion detection data sets, and we implement each scheme using both SRAM and TCAM memory. For this presentation, the metrics we will focus on is the number of table rules and the switch stages, and the classification accuracy on the intrusion detection data set. So let's begin by looking at the SRAM utilization for complete trees using 10 features. So on the x-axis here, we have the number of SRAM table entries required. On the y-axis, we have the number of switch stages required. And in the gray region, we show designs that are not feasible on a Tofino switch. So pforest and switch trees use few table entries, but they're unable to support trees beyond depth 5 because they're limited by the number of switch stages. Easy, on the other hand, uses up a lot more table entries, but it experiences an exponential increase in the resource required. And Leo sits in a good middle ground between both, managing trees of depth 10. So using the same number of stages, Leo is able to support trees that are twice as deep as pforest and switch tree. And if we zoom into the data point for depth 4 trees, Leo and Easy both use 5 switch stages, but Leo manages to support this tree with an order of magnitude smaller table entries. Now let us take a look at the classification accuracy of these schemes in an intrusion detection workload. So we will focus on SRAM and using CIC-IDS 2017 dataset. So pforest and switch tree achieves an F1 score of 67%, while IZ manages an F1 score of 75%. Leo outperforms both schemes by managing an F1 score of 94%, and it comes quite close to the control plane, which not only has access to a very large tree, but it also has access to the full set of features that can be done in a control plane solution. So we have more evaluation in the paper, including results for TCAM, where we show that Leo can support complete trees up to a depth of 13, and it can scale even further to a depth of 22 if the number of leaves are 1024. We also include analysis on the impact of per flow state on the number of concurrent flows that can be supported, and also show accuracy for intrusion detection workloads using a TCAM-based solution. So to conclude, we presented Leo, which is a scheme to support decision trees on programmable switches in an efficient and runtime programmable manner. We find that it is scalable, reaching trees that are twice as deep as the state of the art, and supporting a large number of concurrent flows while achieving a good accuracy. Finally, we make the source code of Leo publicly available. So thank you for your attention, and I'm happy to take questions.